Yes, that way. Cool. Hi, welcome. My name is Jeff Kotz, and I'm here today to talk to you about one sample tests of hypothesis, otherwise known as hypothesis testing. I like to think of it as truth testing, but I'll tell you why in a second. If you're familiar with these slides, then you may also be familiar with this textbook, which is now backwards. It's the instructor edition. Um, Basic Statistics for Business and Economics by Lind, Marshall, and Wathan. Thank you so much for writing the textbook. I find it very useful. If you don't have that textbook, that's okay. I hope in some of these explanations today you'll be able to walk away with some knowledge about hypothesis and truth testing. These are the things that we're going to cover today. We've got a lot to get to. We're going to start by outlining what the steps in the hypothesis testing procedure are. We've got to define a couple of terms. We're going to define test statistics and critical values. We're going to talk also about the two competing hypotheses in a hypothesis test, and that's the null hypothesis and the alternate hypothesis. The three types of problems that we're going to investigate today deal with either testing a mean or testing a proportion in terms of a hypothesis test. In some cases, you know sigma. In some cases, you don't know sigma, and that's if you're doing a mean test. You'll never know sigma if you're doing a proportion test because it doesn't have that standard deviation. Those are the three types of problems we'll cover. When we get through the end of that, we'll talk about the two different types of errors that you can potentially make when you do your hypothesis or truth testing. And lastly, we'll discuss what I think and prefer is a better method for doing hypothesis testing, which provides more precision, and we could call it the p-value method for lack of a better term. Hypothesis testing involves coming up with a hypothesis, a statement about the value of a population parameter developed for the purpose of testing. A hypothesis testing procedure is based on sample evidence and probability theory to determine whether or not a hypothesis is a reasonable statement. So you begin by making a statement about a population parameter, mu or pi. Chapter 13 we'll talk about rho. We're going to make some statement. And then we collect some sample statistics that we're going to use to compare to the population parameter, the initial hypothesis that we met. Now, here's where I call it truth testing, is because you go out and experience the world and collect a sample full of data. And when you take your small quantified piece and compare it to whatever truth you're being told, you may either agree with the truth that you've been told, or you may disagree. So when you set up hypotheses, you set up statements about the truth in the world, and then you collect what you believe is evidence to support or reject the truth that's in the world. The procedure, as it's outlined here, talks about 5 steps. Whether or not you follow these 5 steps exactly, or other reasons why it may change, we're not going to go into in full detail, but I think they do provide a pretty strong framework. You begin by stating your null and alternate hypotheses. We're going to introduce those in just a second. After that, you state a level of significance. In other words, how much error are you willing to accept in the results that you interpret? The third thing you do is identify the test statistic. In our case today, we're going to be looking at either Z or T. Z and T are very similar normal distributions. They have very similar shapes and they accomplish very much the same purpose. The fourth thing we do after we identify the test statistic is we formulate a decision rule. Essentially, that's coming up with a critical or cutoff value. We'll define it here as a critical value, but the critical value is how you define your decision rule. Lastly, you take a sample and collect the data. Once you collect the data, you compare your results from the sample data you collected to the decision rule that you established in the previous step, and then you decide what you do with your competing hypotheses. One of them will be supported and the other won't. The two hypotheses that are competing are the null hypothesis and the alternate hypothesis. The null hypothesis is a statement about the value of a population parameter developed for the purpose of testing numerical evidence. Now, it sounds a lot like the initial definition of a hypothesis, and that's good because this is also a hypothesis. But what's important about this definition is that it's developed for the purpose of testing numerical evidence. The only purpose the null hypothesis will serve is that it allows us to either accept it or reject it. One of those two things. If we accept the null and we say that the statement we make in the null is true, or at least that we accept it or support it with our evidence, then we have to reject the alternate hypotheses. There are two hypotheses. They are mutually exclusive. They do not overlap. And they are collectively exhaustive. They describe the entire space of truth. One of these two things, and only one of these two things, can we support. We develop the null hypothesis as an alternate to the alternate hypothesis. The alternate hypothesis is sometimes called the research hypothesis. It's the question we're asking. It's the thing we think might possibly be true. Well, if we really start with the alternate hypothesis, we're saying this is the thing I want to try to find out. Well, the other thing is the null. Everything else is the null. For example, if I have this bottle here and it's got a certain amount of liquid in it, I can say that there's two possibilities. I can say it's either half empty or half full. If I reject the notion that it's half empty, then it must be half full. Statistically, we do similar things with the null and the alternate hypotheses. When we develop these hypotheses, they may also have a direction or not. A directional hypothesis, such as the ones we see over here on the right, give us some indication of whether or not our research or alternate hypothesis gives us some direction. So we might say, for example, that in this bottle there is more than 20 ounces of liquid. We might say there is less than 20 ounces of liquid. Either one of those, more or less, provides us with some direction. A non-directional hypothesis would say, there could be 20 ounces of liquid in here, or maybe there's not. Now, granted, more than 20, less than 20, those original directional hypotheses, sure, both of those are consistent with the notion that there is not 20 ounces of liquid in here. Both of those directional hypotheses say there could be more or less. But a non-directional hypothesis is much more non-specific. We're simply stating the fact that there is either 20 ounces or there is not 20 ounces. If I can reject the notion that there are 20 ounces in here, I can accept the notion there is not 20 ounces in here. Well, if we go back to the directional hypotheses, we put ourselves in a position, if I hypothesize that there is less than 20 ounces in here, and I find out that there's either exactly 20 ounces or more than 20 ounces in here, there certainly isn't less than 20 ounces in here. So when I have two competing hypotheses in that regard, I might say, one, my research or alternate hypothesis says that, sure, there's less than 20 ounces in here. But everything else, whether it's equal to or greater than, well, both of those do not allow me to say there's less than 20 in here. The null and the alternate hypotheses are always competing, and you can only support one. Those hypotheses, those alternate or research hypotheses, can come in one of two forms. It can be a one-tailed test or a two-tailed test, depending on whether or not it's a directional or non-directional hypothesis. When we do these tests of directional or non-directional hypotheses, we have to come up with two things in order to do the test. One, we have to calculate a test statistic. It is a value determined from sample information. It is when we go out in the world and we gather information and we come together, well, we use our sample information and some special formulas to calculate a test statistic. Test statistics come from formulas. Critical values, on the other hand, are dividing points. When we looked at that picture earlier, the points that we saw that cut off little tails, those are called critical values. They're dividing points between where the region of the region of rejection is separated from the region of acceptance. In other words, whether or not we get to reject or accept a particular hypothesis. In the case of this, it's always the null hypothesis. Critical values, importantly, come from tables. Test statistics come from formulas. Critical values come from tables. Back at the picture we were looking at here earlier, that's the thing that gets mentioned here is the critical value. You establish the critical value as a cutoff between some tail over here and the rest of everything else. Or in the case of a two-tailed test, we can have two critical values, one on the negative side and one on the positive side. In both cases, the middle, this big massive chunk here, if we calculate a test statistic that lands in here, we do not reject the null. A good answer is to say we accept the null. A better answer is to say we fail to reject the null. The null is a statement of equivalence. We'll talk about that. The null is a statement of equivalence. And if we collect enough data, to be honest, and this is a statistical thing, if we collect a massive amount of data, we can detect small differences and we'll always end up rejecting the null if we collect a ton of data. But the concept of accepting the null presumes that we can ever say that things are actually equal, and that's not the case. The best we can do in hypothesis testing is to say we fail to reject the null, which is like accepting it, or we can reject the null. If we gather enough evidence to reject the null, then we get to accept the alternate hypothesis. We get to accept the research hypothesis. We get to accept the idea that we proposed initially. I propose that there is less than 20 ounces of liquid in here. If it's not less than, in other words, greater than or equal to, which is everything else, well, that greater than or equal to is the null hypothesis. Less than 20 ounces, that's my research hypothesis. If I can reject the notion that there is greater than or equal to 20 ounces in here, then I can say there's less than 20 ounces. It's something I can remedy right now. Let's start with the first example. Perhaps some of these terms will become more clear as we go through a series of examples. So we start in Jamestown at the Jamestown Steel Company, which manufactures and assembles desks and other office equipment. The weekly production of the model A325, not to be confused with the A315, easily confused, I know. But the weekly production at the Fredonia plant follows the normal probability distribution, with a mean of 200 and a standard deviation of 16. Recently, we've introduced new production methods and new employees have been hired. We have changed somehow. We have changed the procedures and a bunch of stuff. The vice president of manufacturing now wants to know whether or not there has been a change in the weekly production of the Model A325. So in order to investigate whether or not a change has been made, we collect a sample of 50 weeks. We find out that the mean of those 50 weeks was 203.5 desks, an increase over the baseline, over the initial, which is 200. We're going to test at a specific significance level, 0.01, whether or not this has produced a change. This question illustrates one of the interesting points about hypotheses, at least in terms of their direction. It's very easy to recognize a directional hypothesis because it will say something like less than, more than, greater than, fewer than. It'll give you a direction. Here, the way this is stated, it just says the VP would like to know whether or not there has been a change. It could be more, it could be less. The VP just wants to know that all that crap I did that I said was my job and changing people and changing procedure, did that actually change the number of desks that got produced? Well, when we look at the sample mean here of 203.5, we presume that those changes created an increase. So we might presume it's a directional hypothesis. We can't make that presumption. We must operate on what the question asks, and in this case, it's has there been a change? So we begin by stating our null hypotheses and our alternate hypothesis. We start by saying mu equals 200, and we call that our null. So it's h sub 0, h sub naught, h sub null. It's the null hypothesis. It's a statement about the population parameter. So when we were initially given this problem, we were told that the population has a mean of 200. They know this thing to be true. So we could say, yeah, the mean after we introduce these changes could potentially still be 200. And that's the statement of equivalence. The null hypothesis is always a statement of equivalence. The alternate hypothesis is to say, no, based on my sample data, I might conclude that there is a new population mean, and that new population mean is not equal to 200. Based on my sample data, I think that the changes that the vice president introduced, in fact, has now changed our mean from something that was 200 and is now no longer 200. Your research or alternate hypothesis, sometimes denoted HA, HR, in this case it's H1. That's the question that you're always being asked. Essentially, you start here. This is the question that was asked in the problem. The null hypothesis is everything else. Step 2, select the level of significance. Well, 0.01 is stated in the problem. Select this test statistic. In this case, we use the z-distribution. When we're doing tests of a mean, and we know the population standard deviation, we know sigma, then we're going to use the procedure which involves the z-tables. When we don't know sigma, and we only know the sample standard deviation, we have to use a procedure that involves the t-tables. They're really bad mnemonics, I know, but when you know sigma, you use z, so I just think of the word Zigma, with starts with a Z. It's not really a word, it's barely a portmanteau, but hopefully it's something that will allow you to say, if I have sigma, then I use z. Alternately, if you have S as opposed to sigma, S and T happen to be right next to each other in the alphabet, which makes it convenient because when you have S, you use T. We use the Z distribution since sigma is known. This is the formula for the test statistic. And I'll let you know that the formula for the T statistic is nearly identical. And they're identical in a couple of different ways. When we calculate the T statistic, you'll see that we just substitute S in for sigma. It's not a real big deal. But what we do have here are two very cool things. On the top, we have the difference between the sample mean and the population mean. That thing has a name. It's called sampling error. Sampling error is the difference between our sample statistic and our population parameter. Now, our parameter is given to us. It's the truth. It's the thing they said. This is how the world is, was, or shall continue to be, unless we are given other evidence. On the bottom, sigma over square root of n, that has another name too. That is called your standard error. Your test statistic is always sampling error over standard error. When we do it with Z, when we do it with T, in chapter 13, when we do it, we calculate T statistics for R. Even though the formula looks funny, it's still literally sampling error over standard error. Fourth step is that we need to formulate a decision rule. Now, this is where we come up with critical values in our distribution, which is to say, we begin by taking alpha, and if alpha is 0.01, and in this case we have a two-tail test, we take all of that alpha, 0.01, we cut it in half, and we put half of it in one tail and half of it in the other tail. So essentially what we do now is that we've got critical values out here which establish decision rules. We calculate test statistics. Our test statistic is also in Z units. Our critical value is in Z units. We're going to get that critical value from a Z table, and then we're going to calculate a Z statistic. If our calculated test statistic is over here or over here, then we have a test statistic that is in the region of rejection. Region of rejection of what? Region of rejection of the null hypothesis. Otherwise, we have a test statistic that is in the region of acceptance. Acceptance of what? Acceptance of the null hypothesis. So we fail to reject the null. In order to use our Z table to get a critical value, again, with the two-tailed test, you take all of alpha, which is 0.01, and cut it in half so that we've got an equal amount on both sides. Second, we know that because our Z distribution is symmetrical, half of all of the area lies to each side of the mean, median, mode, this central point. Let's say the mean. So if the whole area here is 0.5, and this little area is 0.005, the area between here and right here is going to be 0.5 minus that number. The reason I'm looking for that area is because that's the area that this table knows. 0.5 minus 0.005 is 0.4950. We cannot find that area in this table, but we can find two values that are close. 2.58 and negative 2.58. It's the magnitude of distance away from the mean that would leave an area of 0.005 in a tail. Now we have critical values. We've been given a sample mean from our 50-week trial of 203.5 desks. Our population mean, which was the truth as the world existed, is 200. We have a population standard deviation of 16 as defined in the problem. We have a sample size of 50 weeks. We know it's a non-directional test because we're just asking for a change. And we've come up with a critical value of 2.58. Now you can calculate, using this formula, a test statistic. And I'll wait. Anyway, moving on. We calculate a test statistic using that formula of Z equals 1.55. X bar is 203.5, mu is 200, sigma 16. Square root of n is about 7. N is 50. Gives us a Z equals 1.55. This number right here. Because our computed test statistic is not in the region of rejection, we failed to reject the null. H naught is not rejected, and we conclude that the population mean is not different from 200. So we've introduced some changes, but those changes haven't changed much. That is to say that 203.5 is still really close to 200. It's not really all that different. Important things to remember now that we've begun to use H naught and H1. This is called the null hypothesis, and H1 is the alternate. H1 and H naught are mutually exclusive and collectively exhaustive. They define the entire space, and there is no overlap, so that if we reject one, we get to accept the other. H1 always has the burden of proof, which is to say, unless we can say otherwise, mu or pi, the population parameter that people tell me is true, I have to believe that until I come up with some sample evidence that allows me to say otherwise. H1 has the burden of proof. We use a random sample to try to reject that truth statement that's given to us. This is something I mentioned a little bit earlier too. If we conclude do not reject H naught, doesn't necessarily mean that we accept it as being true. It only suggests that we don't have enough evidence right now to reject the null. Maybe we just needed a slightly larger sample, and then we could reject the null. But all it says is that we don't have enough evidence to reject it. Equality is always part of H naught. The null hypothesis is always a statement of equality. These inequality parts down here are always part of the alternate hypothesis. But note None of those, that's certainly not equals because it's not equals. Neither of those have the little equal to bar under it like both of those have. There's no equality in H1. There's always equality in H naught. Let's take another example this time. We're still going to be making desks. Apparently, they look like skateboards. But let's say that the vice president, instead of saying, has there been a change in the number of desks produced? Has there been an increase? I am a good vice president. Therefore, if I make changes, I assume that they must cause an increase in the number of desks being made. Let's ask the question that way. In other words, can we conclude, because of the improved production methods, that the mean number of desks assembled in the last 50 weeks is more than 2,000? Well, that's certainly a directional hypothesis because we're talking about more than. We go through the steps of the procedure. One, I think it's probably best to start with your alternate hypothesis. Can we conclude that the new population mean is greater than 200? The null hypothesis, therefore, is everything else. Now, here's a tip. If you draw, as I recommend, drawing the normal curve every time you execute one of these problems, the direction that the inequality in your alternate hypothesis points, that will tell you which side the tail is on. In this case, mu greater than 200 points to the right. I'm going to put my tail for our directional hypothesis on the right. We state the level of significance. That hasn't changed. We still use z because sigma. Before, we had a two-tailed test. We simply said mu is 200 or it's not. Now we say mu is greater than 200 or it's less than or equal to 200. In this case, we follow the same steps that we used with the z-table. We would go and have an area in the tail of 0.01. In the middle, half of the area is to one side of the mean, half of the area is to the other. So this area between 0 and my critical value was 0.49. You look up 0.49 in the body of your z-table. Go to the outside and you'll see 2.33 is your z-value. A little bit more precision provides 2.326. Now that's our critical value. Notice that the tail for the region of rejection of what? Region of rejection of the null hypothesis. It's over here. It's to the right side of the curve, the direction this is pointing. Heck, that thing almost looks like that. What changing it from a two-tail to a one-tail test does effectively is moves the critical value closer to the mean, closer to the middle, which means a one-tail test is, let's say, easier in terms of can we reject the null. We're going to have the same test statistic, by the way, because none of our sample data has changed. Test statistics come from sample data and formula, and if our sample data hasn't changed, when you do it, you still get a test statistic of 1.55. That's still in the region of acceptance, where H naught is not rejected. So we still say that 1.55 does not fall in the region of rejection. Therefore, H naught is not rejected. We conclude that the average number of desks assembled in the last 50 weeks is not more than 500. So whether we ask the question, is it different from 200 or is it more than 200, both cases we end up with the same conclusion. And that's the statement of equivalence that we fail to reject the null. We don't think that these changes have been very effective. A third type is if we have a population standard deviation unknown. I mentioned this earlier. When you know sigma, then you get to use z. But if you don't know sigma and you only have the sample standard deviation s, you have to use the t distribution. And it looks just like that z formula we looked at before, but instead of sigma, there's s. When we use the t-table looks awfully different from the z-table. Let me give you an example of how we might use this. The McFarland Insurance Company Claims Department reports that the mean cost to process a claim is $60. Anytime they tell you this is the case, that's what you can presume your population parameter is. An industry comparison showed this amount to be larger than most other insurance companies, so the company, McFarland Insurance, instituted cost-cutting measures. This needs to go down. To evaluate the effect of these cost-cutting measures, the supervisor of the claims department selected a random sample of 26 claims, and they're down here, and the sample information is reported. At the .01 significance level, is it reasonable to claim that we've done enough, that the cost to process a claim is now less than $60? Well, if you take that information from those 26 claims, we find out that the sample mean is $56.42 and the standard deviation is right around $10. Given that information, and given the fact that we don't have population standard deviation given, if they had given us population standard deviation, we could use Z. But the only thing that tells us about the population is the mean, which is 60. We recognize that we can't use Z because we don't have sigma. We have to use the sample standard deviation, symbol is S. S is close to T, and that's good because we need to use the T table. Step 1, set up our hypotheses. First, our research hypothesis. Well, that's mu, our new population mean after we institute these changes. Is it now less than $60? The null hypothesis is everything else. Step 2 is the level of significance that's given as alpha equals 0.01. Second, third, select the test statistic. Here, since we don't have sigma and we only have S, we have to use T instead of Z. The other part that we need to know, and this is specific to the case of using T, is we need to know for the T distribution degrees of freedom. I'm not going to go into an in-depth discussion about how that works. I want to talk a little bit about the T table, though, and how it works. See, the T distribution and the Z distribution are quite similar in terms of their shape. But when you have a very small sample size, then your T distribution has much fatter tails. They're further off of the x-axis, and it appears to be less asymptotic. It's much flatter, it's more platykurtic, and the tails are thicker. But as that sample size gets larger, it begins to look more and more like the Z distribution. So for large sample sizes, T and Z are very similar, almost the same, you could say. But for small sample sizes, let's say under a couple hundred, we see a lot of variance under 100, then we need to make sure we take that into account in terms of the amount of area in the probability distribution that we have. In order to use the t-table, we need 3 pieces of information. And this is to find our critical value. Test statistics come from formulas and sample information. Critical values come from tables. The 3 pieces of information we need in order to use the t-table is our alpha level, our knowledge of the number of tails, and our degrees of freedom. Degrees of freedom has a simple formula. It's for the t, it's n minus 1. We had 26 claims, n is 26, 26 minus 1, 25 degrees of freedom. Degrees of freedom, again, informs us about the shape and the width and the kurtosis of our t distribution. 3 pieces, alpha, tails, and degrees of freedom. How we use the t-table? Well, we go to the header row here. We've got 3, one for confidence intervals, we've discussed earlier, level of significance for a one-tailed test and level of significance for a two-tailed test. I know it's a one-tailed test with an alpha level of 0.01. So in the header row that says one-tailed test, I go to my alpha level of 0.01. This is the column that I'll be using exclusively. Second, or third at this point, third, degrees of freedom is 25. We calculated that. Where those two things intersect is 2.485, and that's our critical value. It's our critical value because it came from the table. A one-tailed test when alpha level 0.01 and 25 degrees of freedom yields a critical T 2.485. Now that we've got a critical value, which has established our decision rule, we can use our formula here to calculate a t-value using our sample data. When you do that, you will see that, wait a second, I thought our t-table said that our critical t was 2.485. Why is this one negative? If we go back to our hypothesis, our alternate hypothesis points towards the left. It's a one-tail hypothesis, and it's presuming, or we're hypothesizing, that these cost-cutting measures have gone where we were initially and reduced, that we're negative, that we're going to lower the cost. Why I always recommend drawing the pictures, you can draw the tails on there, is so you don't screw up the sign of your critical value. When we calculate our test statistic, we get negative 1.818. That is not less than negative 2.485. It remains in the region of acceptance. The region of acceptance of what? The region of acceptance of the null hypothesis. We fail to reject the null. When we went to the t-table, we got a critical value. We put it on the appropriate side of the distribution. We took our calculated value, our test statistic, which we got from our formula using our sample data. We failed to reject the null. This means that our cost-cutting measures have failed to reduce the cost from $60. Now, accepting the null does not mean that it is not true. It simply means that we haven't perhaps collected enough evidence. Maybe a sample of 25 is too small. Maybe if we had a larger sample, perhaps we could move our critical value closer towards the mean and maybe reject the null. Another example here is to say the current rate for producing 5 amp fuses at Neary Electric Company is 250 per hour. We've got a new machine, it's been purchased and installed, and according to the supplier, it will increase our production rate, that we're going to make more per hour. A sample of 10 randomly selected hours from last month revealed the mean hourly production on this new machine to be 256, with a sample standard deviation of 6 per hour. At the 0.05 significance level, can Neary conclude the new machine is faster? Well, we're certainly producing more units per hour, so that's in the right direction. But I don't know, is 256 a lot more than 250? Meaningfully more? Or does it just barely enough that it's more, but not really meaningfully more? Step 1, come up with your hypotheses. Start here. Is the new population mean greater than 250? Hey, that means a directional hypothesis with the tail on the right. Why is the tail on the right? Because the inequality points to the right. The null hypothesis is everything else. The level of significance is declared for us, 0.05. Which test statistic do we use? Well, we don't have sigma, but we've got t. We don't have sigma, but we have s. Because we have s, we got to use t. Well, given our sample standard deviation, our sample mean, our population mean, we've got all this stuff. A sample size of 10 weeks means that we have 9 degrees of freedom for our t-value. It is directional because we said, have we increased? Are there more widgets being produced in an hour? We go to our t-table, we find that our critical value is 1.833. We get there by saying we've got a one-tailed test, the 0.05 significance level, or alpha 0.05, same thing, and 9 degrees of freedom. Where those two things intersect, we find 1.833. Our test statistic is 3.162, which we get by plugging all those numbers from our sample data into our formula. Test statistics come from formula and sample data. Critical values come from tables. Now we get a chance to interpret our results. Well, 3.162 is in fact greater than 1.8. Hey, we get to reject the null because our test statistic is outside the region of acceptance of the null. It's in the region of rejection. We reject the null. Null means no relationship or no difference. The null is a statement of equality. We reject all of those things. We reject equality. Here, we reject equality. We reject equality in terms of the old mean is still the new mean, that the old mean of 250 is no longer equal to whatever our new mean is. Our sample suggests that it's 256 widgets per hour or whatever it is. That's an estimate of what we believe the new population parameter to be. It's probably pretty close to 256, maybe more or less. But based on this information, we can say that we have definitely got more than 250. We reject the null. Our new mu is greater than 250. We can also do tests that don't just talk about means. We can do tests that talk about proportions. A proportion is a fraction or percentage that indicates part of the population or sample having a particular trait. Your sample proportion, denoted p proportion, is found by x over n, where x is the number of things that have the characteristic you're looking for, and n is the total number of things ever. Same formula as before. Wait a minute, it doesn't look like the same formula. Hear me out. On the top, we have the difference between the sample statistic, the sample proportion p, and the population parameter pi. P and pi are both parameters. In one case, it's a sample statistic. In the other case, it's the population parameters. Sorry, P and pi are both proportions. We get the p's mixed up. P and pi are both proportions. P is a sample proportion. Pi is a population proportion. The difference between your sample statistic and your population parameter, that's sampling error, and that's on top. This down here, well, that's the standard error of proportion. We've seen it earlier using p's. We had to use p like chapter 8 or 9 or whatever because we didn't have pi. When you have the population proportion, you may as well use it. We still have sampling error over standard error for our test statistic, and our test statistic for proportions is z. Yeah, but it's basically plugged that stuff in there. So here's an example. Suppose prior elections in a certain state, which looks like Florida, indicates that it's necessary for a candidate for governor to receive at least 80% of the vote in the northern section of the state in order to be elected. The incumbent governor is interested in assessing his chances of returning to office and plans to conduct a survey of 2,000 registered voters. A sample of 2,000 potential voters in the northern part of the state revealed that 1,550 planned to vote for the incumbent governor. Using the hypothesis testing procedure, assess the governor's chances of re-election. This problem can be a little tricky in terms of setting up our hypotheses, but let's take a look right off the bat. We have to test the notion that our population parameter is less than 80%. Why 80%? Well, because that's the number they told us we needed. Had we set this to a research hypothesis, an alternate hypothesis, pi greater than 80, well, that would test something different. I know I need at least 80. At least 80 is 80 or above. Had I done pi greater than 80, well, I wouldn't have tested whether I have 80 exactly. I would really be testing, am I going to win in a landslide? The way this hypothesis is set up, it says, if the research hypothesis is supported, I'm in danger of losing the election. I know that with less than 80, I should be worried. If it's not less than 80, which is greater than or equal to, then I don't really have to worry. But I should be worried if it's less than 80. If you flip these around and say pi greater than 80 for the research hypothesis, pi less than or equal to 80% for the null hypothesis, that second, the one that's not listed here, that's do you win by a landslide, or mutually exclusive and exhaustive, do you potentially win or lose? Win or lose versus win by a landslide, as opposed to here, which says in danger of losing or probably going to win. The alpha level is 0.05 as stated in the problem, and we use the z distribution here. And for the problems we'll be looking at, this is a logic test that I'll make sure for our problems are all kosher all the time, but we will be using the z distribution. We calculate a test statistic here, z. P is 0.775. How did we get that? Well, that's 1550 over 2,000. 1,550 plan to vote for the incumbent governor out of the 2,000 that was surveyed. That creates a sample proportion of 0.775. Pi is given in the problem as 0.8. Our sample was 2,000. This is, in fact, a directional hypothesis. We get a critical value of, we put one tail over here. One tail with an alpha level of 0.05 gives us a critical value of 1.65. Looking up 0.4500 here. Critical value of 1.65. Negative because it's on the left. Now we do it again. We calculate a test statistic, which we can then compare to our critical value. Our test statistic is in the region of rejection, so we reject the null. Because our z of negative 2.8 is in the region of rejection, we reject the null and we accept the notion that the true population of proportion of people who are going to vote for the incumbent governor is in fact less than 80%. With less than 80% of the vote in northern Florida, the incumbent governor should be worried that he or she will not be reelected. To this point, we've done a number of different hypothesis testing examples, truth testing, if you will. In some cases, our tests might lead to errors. Now, I've included on my Sakai website the information in there about some other alternate videos which are really, really useful in terms of looking at this. But I want to just give a brief idea of how this stuff works. The way I think of these two types of errors, type 1 error, also denoted as alpha, which is also the significance level of this test. I think of this as an error of arrogance. I think of this as an error of ignorance, and I'll tell you why. So let's start by saying that in reality, H naught can be true or H naught can be false. If the null hypothesis is in fact true, so this is reality. Let's say we've got some true access to reality and we know whether or not it's actually true. And we fail to reject that true hypothesis. We have made a correct decision. In reality, H naught is true. We don't reject H naught. Awesome, we're right. Let's say, however, H naught is false. We should be rejecting the null. And hey, when we do, we've made the correct decision. That's fantastic. So in one diagonal here, we've made correct decisions. But we might make errors. The one I call an error of arrogance is type 1 error. Well, first of all, alpha, it's got a A shaped like an A, like arrogance starts with. If you haven't noticed, I like things that alliterate. I think of it as an error of arrogance because generally when we talk about our research findings, it's a result of rejecting the null, that you have found a real difference or you have found a real relationship. You found it. And you're going to walk around saying, look at me, I found this thing to be true. My research is awesome. I'm brilliant. Well, reality check says that H naught is true and you shouldn't have rejected the null, but you're walking around like you did, like you're awesome. Well, that's an error of arrogance to me. That's the way I see it. The other possibility is that H naught is false. There's a real difference out there. There's a real relationship out there. But I didn't collect enough evidence because I'm a lazy, bad researcher. I didn't do all the things that I need to do. I'm just ignorant at this point. Had I collected more data, I would have surely rejected the null. This is an alternate table of the way that can be described. Type 1 error is also called alpha error. When we set up a level of significance, that's to say it's the level of acceptable type 1 error, acceptable level of type 1 error. How much type 1, how much of this arrogance error am I willing to deal with? Is it real important that I have a small alpha so I'm not likely to be arrogantly rejecting nulls that I shouldn't be? A type 2 error, also denoted. Beta is when you should be rejecting the null, but you're not. Here's a really neat little tidbit that comes out of this. As it turns out, both of these are directly related to sample size. So ignorance means that you didn't collect a large enough sample. Statistically speaking, if you collect a large enough sample, you will always be rejecting the null. When I say large enough sample, I mean you can have a tiny, tiny difference that we wouldn't even perceive as being real. Or when we do hypothesis testing for correlations, it's not even a real correlation. But you've collected so much data that literally an artifact of having collected that much data is that you reject the null. So a large, overly large sample size creates lots of type 1 error. Type 2 error is created by not enough sample. I talked to 2 people. They seemed to think nothing was amiss. So, yeah, I think everything's fine. Maybe you should have talked to a couple more people. Another way that we can get around this, though, is to interpret a p-value. Part of our hypothesis testing procedure says, hey, we've got this thing alpha. Alpha is an amount of acceptable error. We're going to declare it at the beginning of the hypothesis testing process. Once I tell you what alpha is, that gives you a cutoff point to accept or reject. Well, that's nominal. That's yes or no. That's on or off. That's one or the other. The p-value method in hypothesis testing ignores the critical value altogether and instead gives us a number which we can then interpret. The p-value is the probability of observing a sample value as extreme as, or more extreme, further towards the tails, than the value observed, given that the null hypothesis is true. So if you say the null hypothesis is true, if you say that there's no difference, well, what's the probability of this happening by chance? That's what we're doing. In fact, the method is so wicked easy, it just makes more sense to me than having to set up a null hypothesis and accepting or rejecting it. Here's why. If we go back to that second example where we had a directional hypothesis for the Model A325 desks. Directional hypothesis. We failed to reject the null because our test statistic 1.55 was not in the region of rejection. However, the test statistic 1.55, well, it creates its own little tail here, marked with those red lines. The area in the tail right here, that's the region of rejection. The region of rejection establishes the critical value. My test statistic, it cuts off an area in the tail as well. And that's your p-value. If I go to 1.55 in my z-table, I find out that the area between the mean and 1.55 is 0.4394. If I subtract that from 0.5, I get 0.0606, which is the area in the tail to the right of 1.55. That means if I had said alpha, as opposed to saying alpha is 0.01, if I said alpha is 0.0607, I would have rejected the null. The difference between 0.06 and 0.01. That's it. I certainly would like to know that I'm pretty close to rejecting the null. But if I just say I accept or I reject the null and that's it, and then I accept or reject the research hypothesis, that's so dichotomous, that's so one or the other, it's imprecise, it's nominal. I'd much prefer to do more than that. What we do is we take our p-value that we calculated, the area in the tail cut off by our test statistic, and that's what the p-value is, the area in the tail cut off by our test statistic. We put it into a table like this. 0.06 is right here. If we have a p-value that's greater than 0.1, we don't have any evidence that we might be able to reject the null. If we have a number that's here, we go up to A and we say 0.06, that's ours, 0.0606. We go up and we say we have some evidence that H naught is not true. We have some evidence that we can reject the null. If our p-value is here, well, like a 0.04, we have strong evidence to reject the null. If we have a p-value here, 0.009, less than 0.01 as it were, we have very strong evidence to reject the null. If we get a p-value, in other words, an extreme test statistic that's really far away from the mean, leaving the area in the tail to be 0.001 or less, we have extremely strong evidence that we can reject the null. That means the p-value is a continuous measure of how much evidence we have to reject the null, as opposed to just saying it's greater than or less than a critical value. That method, and forgive me if this is a bias, is a bit archaic. What I'm always telling you is, well, first of all, in the event of a worldwide electrical and internet collapse, you won't be watching this video. But I think the last thing you'll be doing is running to a Z or a T table to come up with the critical value. You might be able to, because you have electricity right now, calculate these p-values with particular ease, and then we can, well, just look at this table, and that gives me precise information as opposed to a cutoff rule that I need to do by hand. That's my perspective on it, but enough editorializing. We've been here all day. So here's the example that we mentioned before, and we see that the p-value is 0.0606. It's not less than 0.01, so we don't get to reject the null as set up by the decision rule. But when we looked at it based on this table here, we get to see, well, we have some evidence that we might be able to get to reject the null. One last point on the p-value method. This is enough to stop, even though we're right at the end. When you calculate a p-value, it's the area in the tail cut off by the test statistic. What we've done here is a one-tail test. In the event that you have a two-tail test, your p-value is actually double the area because it has to go in both directions. That hasn't been illustrated here, but let's call it a rule for now that you commit to memory. When you calculate a p-value in a non-directional test, the p-value is the area cut off in both directions. In other words, the area in one tail doubled. Commit that to memory because that'll be useful. You do a problem on this. So the things we covered today, in one final last gasp. We covered the steps in the hypothesis testing procedure. You got to start with your research hypothesis so you can develop the null. The research and null hypotheses are mutually exclusive and exhaustive. If you reject the null, you get to accept your research hypothesis. You come up with test statistics from the formulas and sample data. You use critical values, which you gather from the tables. The critical values are established once you are given an alpha level. Alpha, also known as type 1 error, is the acceptable level of type 1 error, the acceptable level of rejecting the null when you shouldn't. We looked at a number of different types of problems. We looked at testing a mean difference for known population standard deviation and unknown population standard deviation. We tested proportions. We found out about voting in northern Florida. We quickly went over type 1 and type 2 error. Type 1 error is alpha error, what I like to refer to as an error of arrogance. Type 2 error is also known as beta error. It's the error of ignorance when you don't have enough information. And lastly, we discussed the p-value method for accepting or rejecting the null hypothesis, but what I like to think of as a continuous interpretation of acceptable level of type 1 error as opposed to just cutting it off. Folks, there's less than 20 ounces in here, and I'm going to drink the rest of it. Thanks for sticking around. I hope you learned something.